Okay, so now let's get to these examples. Okay, so okay, here we go. So the first one, I'll say compute the following. Compute the following antiderivatives. So here's the first one. We got the antiderivative of x squared plus x with respect to x. So that's not just a simple power function, it's a power function x squared added to the identity function x. So it's a little bit more involved. The second one is the antiderivative of x cubed plus the square root of x. It's the first time we've seen a radical. Part C, we've got the antiderivative of x plus 1 divided by the square root of x. And then the last one, this one is almost deliberately made to be a little bit convoluted just to show you how you can break it down using the properties and make it a little bit easier each time. So it's 4 sine of x plus a fraction, and the fraction has a numerator of 2x to the 5 minus the square root of x all over x. And you want the antiderivative with respect to x. So those are the 4 problems that we'll tackle. I got some space here on the page, so I'm going to start the solution over here. So the first one, we're going to take advantage of this property here that says if you have the antiderivative of the sum of 2 functions, you can split it up as 2 separate antiderivatives taken by looking at each of the functions separately. So we'll do that here. We'll write the antiderivative of x squared plus x is equal to the antiderivative of x squared with respect to x plus the antiderivative of x with respect to x. So it's broken it up into 2 separate antiderivatives. And now we can evaluate them separately. So x squared, well, that's a power function, so we can use the power rule for it. So with x to the n, where n is equal to 2, well, 2 is not the case where n is equal to -1, so you're going to use the top case. You'll just have x to the 2 plus 1 over 2 plus 1. That'll give you x to the 3 over 3. In fact, we've already worked this one out on the previous page. That's no surprise that we got x to the 3 over 3, but nonetheless, you can use the power rule to get that. And I'll add my constant of integration. And I am going to make a comment about the c afterwards, but for now we're going to put it in there just like we normally would. So that's the antiderivative of x squared with respect to x. Then for the antiderivative of x, well, it may help to write it as x to the 1, to think of it as a power function. That's quite often what we did when we wanted to differentiate the function x. We'll do the same thing now. We can treat it as a power function. And then go up to the power rule and say, okay, this is n is equal to 1. We've got x to the n where n is equal to 1. That's not the case of -1, so we're going to use the top rule again. So we're going to have x to the 1 plus 1 over 1 plus 1. So that'll be x squared over 2. So you'll have x squared over 2, and then I guess again we would add a constant of integration. Now, there's something that's weird about this. When we've added a constant of integration for this antiderivative, and then we've added another constant of integration for this antiderivative, that's not really what we want to write. Like we wrote c both times. Who says that the constant of integration, the constant that we get from this antiderivative, has to be the same as the constant we get from this antiderivative? In fact, we might want to distinguish between them by writing one as c1 and the other is c2, because they really are 2 different constants of integration, 2 different constants of integration that came from different places. So with that in mind, we could index them with 1 and 2, and then we might actually say, we can write this as x cubed over 3 plus x squared over 2 plus c1 plus c2. And then I could say, okay, well, this is all the constants added together at the end. And then you might ask a question, well, what are they going to add up to? C1, what is C1? It's a constant. It's all it is. It's a real number that could be absolutely anything, and you know nothing about it. What's C2? It's a real number. It could be absolutely anything, and you know nothing about it. So when you take 2 numbers that could be anything and you don't know anything about them, and you add them together, what can you say about the result? And that is, it could be absolutely anything, and you don't know anything about it. So why not just say that once then? How about we just call this c, and just say we'll have one constant of integration. So then I can just write this as x cubed over 3. Pardon me. Okay. Plus x squared over 2 plus c. And then we just have one constant of integration. We don't need to have two separate constants of integration. Just because we broke an antiderivative up into two separate antiderivatives to make it easier, that doesn't mean we need to have two constants of integration. So typically in the future you won't see me do this. I won't write these down and then specifically take the time to combine them into one constant like that. I'll just put one on at the end. That's typically what you do, and that's what you'll see both me and other people do in general. Okay, so that's part A. We'll go through the next one now. This seems like a good place to stop the clip though.